The question I want you to ask yourself is, would you be able to determine the temperature distribution inside of the slab? So the thing is that in that situation, you have a problem where you're putting heat in, but nowhere in the system is there a temperature set that's defined a reference in the system. Meaning that you really can't determine what the temperature profile would be in that situation. It would be floating, because you're putting in heat flux here and heat flux here, and the temperature profile may take a shape that looks a certain way. You may define the shape, but the magnitude will flow up and down. Now that's a concept that may be clear to most of you. Some of you may not be. Don't worry about it. We're going to come back to it. But the point is that in order to have a constrained heat transfer problem, you have to have the right boundary conditions. So the heat equation in general is very difficult to solve by hand. You're not going to do it. In industry, they use computer software like ANSYS, Cosmos, Algor. Numerous software packages allow you to calculate the temperature distribution in complicated geometries. And basically what the software is doing is what we just did. It's taking many control volumes and it's doing energy balances on each of these control volumes. And in each of those control volumes is defined the temperature. And they make up a temperature point in any of these temperature maps that that are shown here. So we'll talk a little bit more about numerical methods to solve complicated heat transfer problems like this as we progress. But right now we're going to deal with what we can do easily by hand. And what we can do is we can work with the heat equation in reduced dimensional space, one, sometimes two-dimensional, and get analytical solutions. And in one dimension, there's many tricks that we can come up with, like resistive network analogies, which we'll get into in the next lecture, that are very powerful tools that are practical and allow easy back-of-the-envelope type calculations. But in general, I want you to appreciate that the complexity, the difficulty of solving the heat equation, and that when you go out in industry, you get a job, or if you hire someone to do work for you, basically they're going to be using these packages, because in real life problems are three-dimensional, and they're going to be using numerical problems, numerical techniques to solve the heat equation. But there's a lot that you can get done by knowing how to work with the heat equation in reduced dimensions, 1, 2, 3 dimensions. So we're going to focus on simple cases that can be solved quickly with less computational time, saving money and also being able to check more rigorous solutions with such quick computations in simple cases. So let's work through an example. This is example 2.2 in your book. All right, take a little time, get your book out. So what we know is the temperature distribution has this function in an instant of time in a one-dimensional wall with uniform heat generation. So we're going back to our slab example. One-dimensional wall, uniform heat generation. Now I'm telling you right now at the beginning, when it comes to the heat equation, there's two types of problems that you can have. You can have one where the temperature profile is known. And the problem-solving methodology includes taking that temperature profile and plugging it into the heat equation where appropriate to get desired quantities. And there's the second type of problem, which is where you don't know the temperature distribution and you need to use the heat equation in given boundary conditions to solve for it. So this is that first type of problem, where you know a temperature profile is given to you out of a black box, and now we're going to use that to get heat transfer information. And I'll tell you this also, if we know the temperature profile, whether we're given it up front or if we solve for it using boundary conditions in the heat equation, once we know that temperature profile, we can solve for the heat conduction rate anywhere in the material and at the boundaries by applying Fourier's law. So let's move forward with this example. So what we want to find in this particular example, the heat rate entering and leaving the wall, the rate of change of energy stored in the wall, and the time rate of temperature change at x equals 0, 0.25, and 0.5 meters. So we're not going to plug numbers in. We're going to work symbolically here with the concepts that would allow you to plug numbers in and solve this problem on your own. So let's look at what we want to find. Heat rate entering and leaving. I just talked about using Fourier's law, so we're going to apply Fourier's law to solve that, and you'll see that in a second. The rate of change of energy storage in the wall. So what is that? Here we're talking about E prime sub ST. So I don't, sometimes, we made a big leap during this lecture. We went from E in minus E out plus E generation equals E storage, this term. And we went from that to the complicated heat diffusion equation that showed these second order partial derivatives of temperature. But they're the same thing. And you have to learn how to work interchangeably between the simple statement of energy balance and the heat equation, which are the same thing. So for the second one, finding the rate of change of energy storage in the wall, that's saying that we're going to need to think about applying just that basic form of the energy balance, E in minus E out plus E gen equals E stored. But for 3, it says it wants the time rate of temperature change. So now it's talking about temperature instead of energy. So where it talked about energy in number 2, we can work with the general form of the energy balance. But when it talks about temperature, we need the heat equation to solve for temperatures. And that's the difference. They're both energy balances. But the difference between the heat equation and the E in minus E out plus E gen equals E stored energy balance is that the heat equation allows us to determine temperature and how temperature changes with position and time. So the schematic I'll let you draw yourself. Our assumptions for this problem, we have our plane wall. So we have one-dimensional conduction in the x direction. We're going to assume that our medium is isotropic with constant properties, which allows us to take that thermal conductivity out of one of those partial derivatives so that our equation becomes a little neater. And then we have uniform internal heat generation within this wall. And here, instead of Q dot, I had it represented as Q triple prime, but it's still the same, watts per meter cubed. So analysis. Just like I promised, we're going to solve for the energy leaving out, the heat rate leaving, by applying Fourier's law at the boundary, x equals 0. So here we are just applying it, and we're basically taking our equation that we were given for temperature, and we're differentiating it. And it's as simple as that. You differentiate it, you get the temperature gradient, you multiply it times thermal conductivity and times the area, and you get the heat rate leaving the wall. Now the heat rate entering the wall. The heat rate leaving the wall, Q out, same thing, except instead of applying it at the boundary x equals 0, now we're applying it at the boundary x equals L. And once again, we get a relation that comes from differentiating and then applying at the right boundary location. All right, so that was the solution to part 1. Part 2, like I said, we want to find E storage. We want to find the rate of energy storage in the wall. So a lot of times on a test or homework, you're not going to be given this hint that it's E storage. It's just going to say the rate of change of energy storage in the wall. And you're going to have to think about what that means. You're going to think rate of change in energy storage means watts in general, okay, and